Hello there. In this video we're going to begin our discussion on how to graph polynomial functions. In the previous set of videos we've already talked about how to graph linear functions and quadratic functions. In particular, functions of the form f of x is equal to x, g of x is equal to x squared, and we may even know what the graph of x cubed looks like. As we know, we can perform any series of transformations on these functions f, g, and h, but how do we sort of graph a more complicated function of a higher degree? So in this video, we're going to be primarily focusing on linear, quadratic, and cubic functions in order to build a set of properties that is going to be used to graph polynomial functions of any degree and any complexity. Alright, so let's start off with a very basic example of a function for which we should already know the graph of. So the first example, let us consider the function p of x is equal to negative 5x minus 7, which we should already know to be a linear function. We can graph this just by using the slope and the y-intercept, but we're going to avoid that for the moment. First off, this is a polynomial, nonetheless. It's a very basic one, such that the degree of this polynomial is equal to 1 since that is the highest exponent, and the leading coefficient of this polynomial p is negative 5. So eventually we're going to characterize these properties so that the degree of this polynomial is an odd number and the leading coefficient of this polynomial is a negative number. This is going to imply some important properties. So we're going to be talking about end behavior in deep detail. So end behavior is what we mean. So as x tends to minus infinity or as x tends to positive infinity, what happens to the behavior of p of x? Does it get arbitrarily big? Does it get arbitrarily small? Or does it sort of grow close to a particular number? So if we apply our knowledge of what this curve looks like, we know this is going to be downward sloping and have a y-intercept of negative 7. So a sketch of this curve, p, is going to be this curve where the axes are as follows. So we see that as x tends to negative infinity, so as x goes this way, our function is getting arbitrarily close to positive infinity. And as x tends to positive infinity, our curve is going downwards to minus infinity. And keep in mind, infinity and minus infinity are not numbers. They are just ideas that demonstrate that it gets arbitrarily large on the positive and or negative directions. So one can prove that if p is a polynomial such that the degree is odd and the leading coefficient is negative, then these two things will imply that the end behavior has this type of property. Let us look at another function for which we should already be able to know the graph of. So consider the function q of x is equal to 4x plus 3 multiplied by x minus 2. So as we already know, since this is in factored form, we can find the x-intercepts directly from these factors using the zero factor theorem. So if we were to graph this, so this is going to be x and this is going to be q of x, so it's going to have an x-intercept at negative 3/4 and it's going to have an x-intercept at positive 2. So since the leading coefficient is 4 times 1, which is positive, this is going to be a parabolic curve that passes through these points and it's going to be convex. So in particular, let us go with the same thought process as we did before. So the degree of this polynomial q, in this case, is going to be 2, namely 1 plus 1. And the leading coefficient of this polynomial q is going to be 4 times 1, which is going to be 4, which is positive. So again, we have an even degree and a positive leading coefficient. So this is going to allow us to talk about the end behavior of this function. Namely, as x tends to negative infinity and x tends to positive infinity, what is happening to my behavior of q of x? So is it getting big, is it getting small, or is it getting close to something? So if the degree is even and the leading coefficient is positive, and we're talking about a polynomial, then this is going to imply that the end behavior is going to be positive infinity for both. And we see that this does get arbitrarily positive in both the negative and the positive x directions. Now let us introduce another concept that is going to allow us to get a little bit more detail about our function. So let's consider the function f of x is equal to 2x minus 1 squared. So again, we know that the degree of f is 2, and the leading coefficient of f one can find to be 2 squared, which is 4. So again, this is going to be a positive number, and this is, that is an even number for the degree, and this is a positive leading coefficient. So therefore, as x tends to minus infinity, f of x is going to tend to what? So this is pretty much a parabola facing upwards, so this is going to go to positive infinity as well. And as x tends to positive infinity, f of x is going to tend to positive infinity also. So this is our end behavior. So let us see if I can graph this in detail. So I'm going to only have one x-intercept, namely at 1/2. So one should know that the vertex of this curve is going to sort of touch on the x-axis, and we're going to be having this type of shape for f. So how can one know that at the x-intercept it sort of bounces off? So the curve bounces off the x-axis. This can be determined without actually graphing by looking at the x-intercept associated to this particular factor. So this number is referred to as the multiplicity of the 0. So it's always going to bounce off the x-axis if the multiplicity of the factor is even. So what is the alternative to this type of behavior? So consider the function g of x is equal to 3x minus 7 to the power of 3. So in this case, we're only going to have one x-intercept, namely x is equal to 7/3, but here the multiplicity is 3 is odd. So we have 7/3 as our x-intercept, so this is going to be x and this is going to be g of x. So for our end behavior, so we see that the degree of this function g is odd, since it's 3. And the leading coefficient of this function g is going to be 3 cubed, which is positive. So therefore we know the end behavior, as x tends to negative infinity, one can verify that we have, so 3 times minus infinity is going to be a really negative number, minus 7 that's going to be really negative. So as x tends to minus infinity, g of x is going to tend to minus infinity. And x tends to positive infinity, so 3 times a really big number minus just 7 is still a really big number, so that's going to be positive infinity. So it's going to be really negative, really positive, and it has to pass through this point and only that point. So we're going to have a cubic function that has this type of shape. So the end behavior talks about where it's going at the plus or minus infinity directions. And the multiplicity here tells us what is going on locally at 7/3. So the multiplicity tells us the local behavior, and the degree and leading coefficient tells us about the end behavior. So if the multiplicity is odd, then the curve is going to pass through the x-intercept. So let's sort of summarize these things, and in the next video we're going to do some more detailed examples. So let's first off outline the things about end behavior. So we have 4 cases. So case 1, suppose that the degree is even. In case 2, let us assume that the degree is odd. So of course for each of these we have 2 cases, the leading coefficient positive, leading coefficient negative, leading coefficient positive, leading coefficient negative. Alright, so these are our 4 cases. So if the degree is even, that means it's pretty much like a parabola. And if the leading coefficient is positive, then you're going to have something like this. And leading coefficient negative, that means you're going to have something like that. And if the degree is odd and the leading coefficient is positive, you're going to have something like a line going upwards, and leading coefficient negative, you're going to have something that goes down. So these four graphs can sort of give you an idea of what's going on as the end behavior. So as x tends to positive infinity, we see that the function, the y values, is going to tend to positive infinity. Same with the negative direction. Y is going to tend to positive infinity as well. And as x tends to positive infinity, y is going to tend to negative infinity. And as x tends to negative infinity, y will tend to negative infinity as well. So it has the same values regardless of the direction. Now, if we look at the other side of things, so the leading coefficient positive, negative for the degree odd, as x tends to positive infinity, y gets large. But as x tends to negative infinity, y is going to get really negative. And as x tends to positive infinity, y is going to get really negative. As x tends to negative infinity, y is going to get really positive. And notice here, for these cases, these are going to be opposite signs because it's odd. So even has the same sign of infinities on the sides, and odd has the same opposite in behavior on the different directions. And that's the in behavior. So finally, the local behavior at the x-intercepts. So case 1 and case 2. So multiplicity is even, is odd. So if the multiplicity is even, that means you're going to have something like this at some x-intercept. So if the multiplicity is even, this is where we bounce off the x-axis. And if we have a multiplicity odd at a particular point, that's where we pass through the x-axis. So in the next video, we're going to work through a little bit more sophisticated examples that sort of combine all of these things into one type of function.